Hello students, welcome to lecture 16 of the online course on Nanophotonics, Plasmonics and Metamaterials. We will be covering optical properties of metal in this particular course. Now here is the lecture outline. As I mentioned, we will be covering metal optics or plasmonics very briefly, okay. The relevant models to explain the properties of metal, that will also be covered. We will be discussing about the Lorentz oscillator model, we will discuss wave equation and the wave vector k. We will look into the optical properties of an electron gas like that is present in a model metal using Drude model. Okay. So, here is a picture of Paul Carl Ludwig Drude, who was a German physicist, and he has worked towards integrating optics with Maxwell's electromagnetics, and he has forced a theory which is commonly known as Drude model that was able to describe the behavior of electrons in metal. So, that was a very important discovery, and that is why the model is named after him. We will also look into bulk plasmon and different dispersion relations. So, let us move towards metal optics or plasmonics. We have discussed dielectrics till now, and we have understood that majority of the optical components are based on dielectrics. Now, there are a couple of pros and cons with dielectrics. First thing is that dielectrics allow high speed, high bandwidth, but they have a problem that they do not scale well, or you cannot make them very much miniaturized, and that restriction comes from the diffraction limit of light that we have seen in the initial lectures. Other problems would be like bending loss. So, when you bend it, so the modes can actually leak out from these sharp bands, and also if you look here, the diffraction limit allows you to focus light only at a region which is lambda naught over 2 times the refractive index. So, if you look into an optical fiber, that the core size is kind of limited, okay, and it is related to the optical wavelength that it is carrying, and the optical mode in the waveguide will be larger than this. So, there will be some kind of mode extended into the cladding as well. Now, what is the solution going ahead? So, these are some problems we know of dielectric photonics. So, going ahead we can move towards plasmonics or metal optics. So, plasmonic forms a major part of the fascinating field of nanophotonics, which explores how electromagnetic fields are confined over dimensions on the order or smaller than the wavelength. So, this is where you can go sub wavelength. Okay. Now, in the past the devices were relatively slow and bulky. So, we have not seen, most of you have not seen this particular era. We are people of the era of electronics as well as photonics. So, we have seen semiconductor industry which has performed incredibly well to scale down the size of electronics component to nanometer scale. Okay. So, and that is how all these electronic gadgets and devices are becoming sleek, lightweight, compact, and there are more and more electronic devices that is coming to the market. So, miniaturization is very well done by semiconductor industry, but there is a problem with the speed, and we have seen that the interconnect delays in the initial lectures we have discussed it in more details, that the interconnect delays typically restrict the speed of electronic devices to few gigahertz. So, how do you actually go to larger speed? The way is to go for photonics. Now, photonic devices, they have enormous data carrying capacity, but unfortunately these photonic components, they are restricted in miniaturization because of the fundamental diffraction limit of light. Okay. So, you cannot scale them as small as the electronic devices. So, photonic devices cannot be scaled down to nanometer scale because optical wavelengths are in the order of micrometers, right. So, we have to come to plasmonics area where we can have miniaturization as well as the high speed of the photonics. So, this is where Plasmonics offers us the best, that is the size of electronics and speed of photonics. Now, when we talk about Plasmonics, we have to understand what is plasmon. So, researchers have developed that this plasmon can squeeze optical signal into minuscule wires. And how to do it? So, you have to use light to produce electron density waves, which are called plasmons. So, they can be compared, like you can compare electron gas in a metal to a real gas of molecules, okay, and the metals are expected to allow for these electron density waves, which are called plasmons. A simple analogy is like these are like sound waves. So, alteration of air molecules, okay, the way the way sound wave propagates in air, you can think of surface density waves or electron density waves in metal, that is nothing but plasmon. Now, bulk plasmons, they are in the bulk metal. In this case, metals allow electromagnetic wave propagation above the plasma frequency, okay. And there are surface plasmon, where they are also known as surface plasmon polariton, which shows very strong coupling to the electromagnetic field. We have seen this briefly in the introduction lectures, that you can have metal dielectric interface and you can have surface waves propagating along this particular interface, and the field extends more into the dielectric as compared to the metallic region. Now, how do you model this kind of behavior? So, we can actually start modeling the behavior of electron in any material using a spring mass system. So, we can assume that the lattice ions do not move, so they are like big bulky nucleus, okay, and the electrons are connected using a binding force, which behaves more or less like a spring, and we assume that the nucleus or the lattice ions do not move. If they move, you have to use reduced or effective mass, okay. So, this is a kind of simplified assumption that we use. Now, if you take this spring mass damper kind of arrangement for this system, you will see that the damping force can be written as Ft, which is real of F0 e to the power minus I omega t, okay. You can go for the viscous damping given as minus b x dot, okay. X dot is the velocity, x is the displacement, as you can see, x double dot will be the acceleration. So, this is the force. So, overall force is nothing but minus kx, the spring force, minus the viscous damping, this one, minus b x dot, plus whatever is the driving force, okay. So, that is the overall force acting on this system. Now, if you substitute the following, that you define k by m as omega naught square, b by m as gamma, that is collision frequency, and f naught is capital F0, that is the amplitude of the force, driving force over mass, or you can say per unit mass. You can write in this equation takes this particular form, okay. So, if we assume that the time harmonic driving field, then to obtain the frequency domain equation, what you can do? You can use Fourier transform, okay, with e to the power minus I omega t time dependence, where omega is basically the angular frequency, and if you take derivative of e to the power minus I omega t with respect to time, you get I omega e to the power minus I omega t. In few books they call it j omega, I omega, j omega, they are the same thing, okay. Thus, we can easily convert the time domain equation. This is a time domain equation. So, there the first order partial derivative dot dot t can be replaced as I omega, and second order derivatives can be written as this is basically dot square over dot t square, that is nothing but I omega whole square. So, you get minus omega square. So, with that, if you do this apply this into this one, and real part of this is nothing but the cost term. So, if you take x divided by cos term, and if you take that as capital A, you can write this equation in this particular form. Okay. So, I am not going to show each and every term here, you can sit down and find out how it is done, it is very simple. So, finally, you can write A omega, that is how the displacement or the amplitude, okay, of the displacement is moving, okay, and this is in frequency domain. So, you have got f0 over omega naught square minus omega square minus I gamma omega. So, this is the equation you have obtained. Now, we can also write in terms of the restoring force. What is the restoring force here? So, restoring force is minus m omega naught square x, that is the restoring force. Okay. You can write in terms of damping. The damping is nothing but minus m by tau, or you can say 1 by tau is basically the collision frequency. So, tau is the relaxation time. So, minus m by tau x dot, or you can write minus m gamma x dot. Okay. And when you equate this with the, okay, one more term is left, that is the driving force, which is the local electric field. Say if you have got electric field in say the electron will be polarized by this electric field. Okay. So, usually what happens when the electric field is in the positive direction, the cloud will be moved downwards. When the electric field goes in the downward direction, the electron cloud will be pushed upwards, because electric field will get repelled, now the electron cloud will be get repelled by the electric field. Okay. So, you can think it in that direction. So, you can write F driving equals minus E is the electron charge and the local electric field. This you can convert into the time dependence, you can write here, and finally you can put the equation of motion, that is in this form. You can write that ma, this is the force. So, ma, acceleration is written as x double dot. Okay. What are the forces? Spring force, then damping force, that was the viscous force in the previous case. Okay. Here you have seen viscous damping, so that is the damping force. So, here also you have the damping force component and the driving force. Okay. So, these are the three forces when you put them together, okay, in the presence of an electric field, because here the driving force is from the electric field. Okay. So, when you do this, you can find out xt, that is the displacement in time domain, can be written as this one. Okay. E by m over omega naught square minus omega square minus I gamma omega. Okay. And the localized electric field is also time varying. Okay. So, with time it can change, accordingly the displacement will also change. So, from that you can actually find out what is the induced dipole moment P. P is nothing but minus Ex, E is the electron charge. Okay. And then if you have n number of electrons per unit volume, you can write down polarization, which is capital P, as n of this induced dipole moment, and you can put this equation here. X you can write in terms of this, okay, and you can obtain this particular equation. So, here what we can see, that this polarization can be written as epsilon naught chi E. What is chi? Chi is the susceptibility of that particular material. Okay. Now, remember that in general this local electric field is not same as the applied electric field, because this local electric field usually is an average over the different atomic sites, not over the region between the sites. So, there may be slight difference, but in metals the conduction electrons are not bound. Okay. So, they are allowed to freely move around. So, you can feel a macroscopic field of E on average. So, in metal you can safely take that these two things are equal. Okay. Now, from that we arrive at a desired result. We know that the value of permittivity is nothing but 1 plus susceptibility, and this susceptibility is what we got from here. Okay. So, this term we have correlated with epsilon naught chi. So, you can find out what is chi here and you put it in this particular equation. So, chi is nothing but n e square, n is the number of electrons per unit volume, E is the electron charge, m is the electron mass, and epsilon naught is the vacuum permittivity, and this is what you have got. So, from this you can obtain what is the real part of the permittivity. So, there is a imaginary here. So, if you take the conjugate and multiply it on top and bottom on numerator denominator, you can get the denominator completely real and then separate out the two parts. So, a bit of algebraic maths here, and you will be able to find out what is the real and imaginary part of the permittivity. With that, if you try to plot this as a function of frequency normalized to omega naught, you will see this particular graph. So, the red line here, or the red curve, corresponds to the real part of permittivity, and the blue one is the imaginary part, and this is the permittivity and this is the corresponding reflection curve. So, let us see region by region what happens. Okay, let us look into the different regions. So, first one is region 1, as you can see here, where omega is considered much lesser than omega naught, that is this particular region. So, in that region, look at the blue curve is almost 0, that means the imaginary part is almost 0. And what you see that that epsilon 1, that is the real part. So, this is called epsilon 1 and this is epsilon 2 in this particular plot. So, you can see epsilon 1 is greater than 1. So, it is behaving like a transparent material. So, here also you can see in the reflection transmission regime, you can see that this region is basically transmissive region. So, light can easily pass through. Now, let us look into the second region, which is basically of the order. So, it is close to 1. It means omega over omega naught is close to 1. It means frequency is of the order of omega naught. So, in this case, what you see that in this region your material is highly absorptive, because the imaginary part of the permittivity is very high. So, you can denote this region as A. And what is the good thing here? You can see that gamma is the collision frequency, okay, or you can say damping constant, and this width of this region is basically 2 gamma. Okay. In region 3, we are considering omega is much greater than omega naught, that is this particular region. Here you can see that again the imaginary part is much smaller. But in this case, you look at the real part is basically negative. It means in this region the material will be reflective. So, you can see here it is showing reflection. Okay. And in region 4, you can actually see this is region 4, where omega is much larger than omega naught, and we have taken omega to be greater than square root of n e square over m epsilon naught. That will define this term, what is this particular term, and we have seen that in this particular region the imaginary part is almost 0 and the real part is greater than 0. That means the material again becomes transparent. So, these plots are actually done for these values of gamma. So, gamma is taken as 0.2 times omega naught, and omega p, where omega p is this particular frequency where this real part crosses 0. Okay. So, this is taken to be roughly 2. Okay. So, here it is. So, omega p over omega naught is roughly 2. So, that is the case considered here. Now, with that, let us try to see how we describe the optical properties of an electron gas in metal. So, that was the generic model for electron in any material, but in case of metal, most electrons are free because they are not bound to any nucleus. In that case, one important term, that spring term or the restoring force term, that becomes negligible. It means there is no natural frequency of oscillation that was actually given by omega naught. Okay? So, you can take omega naught to be 0 in the case of metal. So, Drude model is very simplified version of the Lorentz model, where you can nullify this particular term omega naught. So, if you simply remove this term, what you are left with is called Drude model. I hope that is clear. So, Lorentz model actually tells you the electron optical property of electron in any material, and then if you put this approximation that bound charges are not there in metal, omega naught, the natural frequency becomes 0. So, you can actually write epsilon omega equals minus 1 minus n is square over m epsilon naught 1 over omega square plus I gamma omega. Okay. So, in this case, this particular term is taken as omega p square, or the plasma frequency omega p can be written as square root of n square over m epsilon naught. Okay. And in that case, this equation looks like this. So, epsilon omega is 1 minus omega p square over omega square plus I omega gamma, or I gamma omega. So, again this epsilon omega has got real and imaginary part. So, you can separate out the two components. So, real part or real components are named as epsilon 1 and imaginary part are named as epsilon 2. So, this actually tells you about the broadening at the loss or the absorption capability of a particular metal. Okay. So, you can also replace gamma by the time constant or the collision time, okay, and you can replace gamma by 1 over t and get this particular equation as well. So, they basically convey the same meaning. Now, this we have already seen that this is Drude model, omega p is given by this, real and imaginary are written like this. Now, let us try to see that in what region how the metal is behaving. So, if you consider omega, which is much lesser than the collision frequency, okay. So, tau is what? Tau is relaxation time. Now, relaxation time, how do you define it? It is the time for the electron between the two collisions when it is roaming around in the lattice. So, inverse of the time is nothing but the collision frequency. Okay. So, if the frequency is much lesser than the collision frequency, in that case you will see that your epsilon 2 is much larger than epsilon 1, means the imaginary part will dominate. It means the metal behaves like absorptive metal. Okay. It's a absorptive property of the metal in that case. Now, if you take frequency which is much larger than the collision frequency but lower than the plasma frequency, in that case you will see that your epsilon 1 is much larger than epsilon 2. It means it is the material or the metal is not absorbing that much. Okay, the absorption is minimal. And if you find that epsilon 1 is basically negative, it means the metal is basically reflective. And this also tells you why metals are shiny. When you see something shiny, it means it is reflecting very strongly. So, electrons in metal follow the oscillating electric field and basically it cancels it. As a result, the electromagnetic fields are not able to enter the metal, okay, and gets totally reflected, and that is why metals are always shiny. You can look at your silver or gold ring or any other metal for that matter, and you will see that it is more or less reflecting in the visible wavelengths. Okay. Now, if the frequency is larger than omega p, we have seen what happens, right? In that case, your epsilon 1 becomes much larger than epsilon 2. It means again the absorption is minimal, but in this case, because epsilon 1 is positive, it allows the light or wavelength to pass through. That means it will become transparent. Okay. When the external field oscillates too fast, that is when the frequency becomes larger than the plasma frequency of that particular metal. So, what is this frequency? This is the frequency of the electromagnetic field that is falling on that metal. Okay. And omega p is the plasma frequency of that metal. So, the metal loses its reflectivity, it is not able to reflect it back, okay, rather it gives up and it allows light to pass through. So, alkali metals such as lithium, sodium, they actually shows this kind of transparency, and these are known as ultraviolet transparency. So, these high frequencies are typically in the ultraviolet range, but noble metal, they do not show this transparency due to interband absorption. So, noble metal like gold, silver, copper, they will not become transparent at this wavelength because they actually absorb, they do not let the light pass through. Okay. So, this is the diagram of permittivity versus frequency, and you can see where it crosses 0, it is basically the plasma frequency. Now, we are actually discussing when the frequency is less than omega p, it means the metal will retain its negative permittivity, that is it will be reflective. So, that is the metallic character. Now, for large frequencies close to omega p, we will see that the product of omega tau is much greater than 1, that leads to negligible damping. Okay. And in this case epsilon omega will be predominantly real, because there is no damping is negligible, means that imaginary part is also negligible. So, you can simply write epsilon omega as 1 minus omega p square by omega square, and this is this particular graph. So, why it is crossing 0 at omega equals omega p, you can see from here. So, if you take omega equals omega p, this term becomes 1, so permittivity becomes 0. Okay. So, this is basically the case as the dielectric function of undamped free electron plasma, because there is, we are ignoring the damping term here, gamma term here. Okay. Now, these are certain values that is important to kind of remember, that the relaxation time of most metal, that is tau, is in the order of 10 to the minus 14 second. So, from that if you find out what is gamma, gamma is basically 100 terahertz, or in energy you will see it is around 0.4 electron volt. Okay. So, mass of electron, charge of electron, okay, mass of electron, charge of electron, density of electron in case of gold and silver is this one, 6 into 10 to the power 28 per meter cube. You can see how many electrons are there in 1 meter cube of gold and silver. Permittivity and all these values are already known to you. Now, what is this? Omega p turns out to be 10 electron volts. So, it is typically in the ultraviolet range. Okay. And you can see this is much larger than the collision frequency. Okay. So, you can actually see this approximation is fine. Okay. Now, if we consider the regime of low frequencies, it means where omega is much lesser than tau inverse or gamma. If we consider that particular case, here you will see that your imaginary part is becoming much larger than the real part. That means the real and imaginary part of the complex refractive index are now also getting comparable. So, from the imaginary part, real and imaginary part of the permittivity, you are also able to find out the real and imaginary part of the refractive indices, that can be written as n and kappa. Okay. And you can see that they are more or less having equal values in this kind of case. So, it is square root of epsilon 2 by 2, and you can write it as square root of tau omega p square over 2 omega. Okay. And in this region the metal is mainly absorbing, because epsilon 2, the imaginary part, is much larger, and it can be defined using a absorption coefficient alpha, that is given as 2 omega p square tau omega over c square and square root of that. We are not going to the derivation of each of this because that will be time consuming. I just want you guys to understand the physics, that in what region the metal is reflective, in what region it is absorptive, and that's how. Okay. So, that will tell you the overall behavior of the metal in a particular electromagnetic field. Now, by introducing the DC conductivity sigma 0, you can write sigma 0 as n square tau by m. Okay. And that can also be correlated to the plasma frequency by this formula, omega p square tau over tau times epsilon naught. So, once you know that, you can put this into your absorption coefficient formula, and you can find out that alpha is square root of 2 sigma naught omega mu naught. Okay. Now, this alpha actually allows you to find out the skin depth. Okay, by application of Beer's law, okay, or Beer-Lambert law of absorption, it implies that for low frequencies the field falls off inside the metal as e to the power minus z by delta. So that is happening in low frequencies. So e to the power minus z by delta. What is delta? Delta is the skin depth. So skin depth delta is defined as 2 over alpha, and you can write it as c over kappa omega. So kappa is this imaginary part, okay, in the refractive index, and you can finally write it as square root 2 over sigma naught omega mu naught. Okay. Now, if you look at higher frequencies, that is in the case when omega tau is larger than equal to 1, but smaller than, it could be smaller than equal omega p tau. If this is the range of the frequencies, you will see the complex refractive index is predominantly imaginary. Okay. It means in that case reflection coefficient R will be almost 1. Okay. And sigma, that is the conductivity part, acquires more and more complex character, and that will blur the boundary between the free and bound charge. Okay. So more or less you can actually use the same model for both the cases. Now our discussion up to this point has assumed that in ideal free electron metal, we will briefly compare the model with an example of real metal important in the field of plasmonics. So let us take one example. So in the free electron model, we know that epsilon goes to 1 when your frequency is much larger than omega p. So you can actually take noble metals like gold, silver, copper. Okay. An extension to this model is needed in the region when omega is greater than omega p. Okay. So this is the region where the response is mainly dominated by the free electrons. So this residual polarization due to the positive background of the ion cores, they can be described by adding the term P infinity. Okay. So that can be written as epsilon naught times epsilon infinity minus 1 times E. So what is P here? This represents solely the polarization due to the free electrons. Okay. So what you are finding out, you are able to find out the contributions from both free electrons and the background. Okay. So the effect therefore is described by a dielectric constant of high frequency, which is called epsilon infinity. Okay. And usually the value of epsilon infinity is from 1 to 10. So instead of 1, you can actually, so 1 minus this was for the free electrons only, but at high frequency there is a background. Because of that you will get this permittivity, okay, from the positive background. So you can write that as epsilon infinity. Okay. So this is the final equation that should describe the permittivity properties of electrons in metal. So this is the Drude model. Okay. So you can see the validity limits of the free electron description in the case of gold. So this particular curved line and these dots are the experimental ones. So you see after a particular frequency range, okay, this free electron description, which was with 1 minus this, that fails very badly. Okay. So till here it is fine, but after that the background plays an important role. Similarly, in the case of imaginary part also, up to this, the free electron one means 1 minus omega p square over omega square plus I omega gamma, okay, that is doing decently well, but as soon as the region of interband transitions enter, okay, you are not able to see a good fit with the experimental data and the free electron description. So you should actually use this particular model that covers the entire thing. So these red dots are basically taken by experimental data measured by Johnson and Christie in 1972. This is a very old paper, but this is one of the most highly cited papers in this field, because they are the first one to measure the dielectric constant of gold and silver and copper, okay, and this was the starting point of plasmonics research. Now, interband transition limits the validity of this model at visible and higher frequencies that you have seen. So, higher the frequency, this model will get increasingly bad. Now, clearly at visible frequencies, the application of free electron model breaks down due to the occurrence of interband transition, and this interband transition actually gives rise to epsilon 2. Okay. Now, with that, let us move to the dispersion layer. So, now we know how to describe the permittivity or the material property of any dielectric using Lorentz model, and we have seen how to do it for druid metals. Okay. And now, let us look at bulk plasmon. Okay. So, what are the dispersion relation of bulk plasmon? So, the physical significance of the excitation at omega p. So, let us consider the collective longitudinal oscillation of the conduction electron gas versus the fixed positive background of the ion cores in a plasma slab. So, this kind of slab you can think of where the electrons are electron cloud is kind of dislocated by U. In that case, sigma can be the charge density. Okay, you can write it as plus NEU. Okay, so a collective displacement of the electron cloud by distance u leads to a surface charge density sigma given as plus minus NEU at the slab boundaries. Now, the electric field inside the slab can be defined as E equals sigma by epsilon naught. Okay, and the restoring force applied to an electron is F, and that can be written as minus small e, that is the charge of electron, and the electric field that has been applied. So, from that you can also write down what is the equation of motion here. It is m a is this particular force. Okay. So, m x double dash can be written as minus n square by epsilon naught times x. Okay. So, resonance frequency is nothing but omega p, that is the plasma frequency, which is square root of n square by epsilon naught m. Fine. Now, let us take turn to describe the transparency regime, which is omega greater than omega p for the free electron gas model. Now, the dispersion relation for the travelling wave can be obtained in this form. So, you have omega epsilon r, omega square epsilon r equals C k. Okay. So, what is this particular formula? If anyone is able to guess, this formula is nothing but what is the dispersion relationship? Omega equals C k, right, in vacuum. Now, omega equals C by or C by n into k, that will be the relation in any medium with refractive index n. So, instead of n you can also write it in terms of permittivity, you can write square root of epsilon, right. So, in that case if you take square on both sides you can get this equation, which is omega square epsilon r equals c square k square. And you also already know that in this region, that is this transparency region, you can actually write epsilon r, that is the relative permittivity, can be written as 1 minus omega p square by omega square. So, when you put this one into this equation, you will get this is your dispersion relation of the travelling wave, because this is the transparency region. Okay. So, the region is plotted for a generic free electron metal. So, you can see this is this particular dispersion relation. So, this is the normalized frequency curve. So, omega over omega p, and this is the wave vector k c over omega p, and this is basically light line. Okay. Now as can be seen, when omega is less than omega p, that is in this region, okay, so propagation of transverse electromagnetic wave is not allowed, okay, into the metal plasma. And when it is above this particular region, okay, plasma supports transverse wave propagating into the inside the metal. And what will be the group velocity in that case? It is Vg, which is d omega by dk, and you can say that it is less than c. So it is all in this particular case. So this is the plasma dispersion. Okay. So it is clear that electromagnetic wave propagation is only allowed for omega greater than omega p. This is the boundary. So this is where exactly omega equals omega p. So anything above that, the electromagnetic wave propagation is possible. Now the significance of the plasma frequency omega p can be further elucidated by recognizing that in the small damping limit, you can write that epsilon at omega p becomes 0 for k equals 0. Okay. So this is the case, right. So both are 0 in this case. This excitation must therefore correspond to a collective longitudinal wave, and in this case you can write that d equals 0, okay, which is epsilon naught E plus P. So from that we will see that at the plasma frequency, the electric field is a pure depolarization field, that is electric field will be minus P over epsilon naught, okay, and that is the essence of plasma frequency. Now this was the dispersion relation I was talking about in the previous case. So for different dielectric like free space, where you can take epsilon equals 1, these are basically epsilon r, okay, do not mistake it, these are epsilon r, okay. I am just writing epsilon here as a short form. So k equals square root of epsilon by c times omega. So if you take epsilon equals 1 for air, this is omega equals ck. This is this particular solid straight line. Now if you consider silica and you want to see what is the propagation inside that, okay, and find out the dispersion, you put epsilon equal to 2 here, you get this particular dispersion relation, okay. So omega is around 0.7 ck, that is this particular dotted line, okay. So in this case, remember that the permittivity or the dielectric function of silica is assumed to be non-dispersive, means it is assumed to be a fixed value for all the wavelengths, but actually it is not like that. But however, the importance here is to show that if you have a dielectric constant larger than air, the slope of the dispersion curve is reduced. And in the case of metal, you can consider this one, where epsilon omega is 1 minus omega p square, okay, the 2 is not visible clearly, omega p square by omega square. So if you put this value here, you actually get this one, you take square on both sides, so you will find omega square equals omega p square plus c square omega square. So this is the dispersion relation in metal. So this is how the wave propagation has to satisfy this condition that you have seen before, that omega has to be greater than omega p for the plasma to be able to propagate, okay. So slow group velocity, obviously, because you will get Vg which is lesser than c. You will also find wavelengths which are longer than the wavelength of light, because you are able to get k values for the same one. So you are getting k values larger than k naught, and asymptotically this will approach the light line when omega goes to infinity. So somewhere down there towards infinity, these two lines will kind of merge. So what is important to remember here is that you will get slow group velocity. How do you get group velocity? You take dou omega by dou k. So if you calculate that, you will see that in this case it is c, in this case it will be smaller than c. So, metal will have or support a lower or slower group velocity, and for the same frequency it will also support long wavelengths because the wave number is larger. Okay. So, k is greater than k naught. Okay. K naught is the one in the vacuum. So, k will be the one in the metal. Okay. So, k is larger. To check this, looks like there is a typo, but yeah. So, it also can support long wavelength. Okay. So, with that we will stop here. So, in the next lecture we will look into the surface plasmon polariton fundamentals, and if you have got any query regarding this lecture, you can drop an email to this particular email address. Thank you.